Falcon 1 failure. On March 20th, 2007, SpaceX's second Falcon 1 rocket lifted off from Amalek Island. The mission ended in failure due to a small but critical weakness in the propellant system. The culprit was a corroded aluminum nut inside the first-stage fuel line. In a marine environment like the Marshall Islands, salty air accelerated corrosion, weakening the fitting over time. When the rocket ignited, the corroded nut failed, releasing kerosene fuel into the engine bay. Liquid kerosene under pressure can ignite easily in the presence of hot surfaces, and the leak caused a fire to spread. The fire damaged engine systems and reduced thrust below the level needed for stable flight. Without enough upward acceleration, the rocket veered off trajectory and eventually fell into the ocean. This highlighted the extreme sensitivity of rocket systems to even the smallest part. A nut no bigger than a finger was enough to destroy a multi-million-dollar launch. To correct the issue, SpaceX switched to stainless steel and titanium hardware, materials more resistant to corrosion and better suited for cryogenic propellants. Falcon 1 collision. On August 2, 2008, Falcon 1 Flight 3 failed during stage separation. The first stage performed well, but separation timing was miscalculated. After engine shutdown, the first stage retained a small amount of residual thrust. This happens because rocket engines don't cut off instantly. Burning propellant continues for fractions of a second after shutdown. Separation was triggered too early. The first stage was still pushing forward as it detached, causing it to physically bump into the second stage. This collision destabilized the upper stage and prevented its engine from igniting correctly. Without a functioning second stage, the payload, including NASA's Trailblazer satellite, was lost. The physics of stage separation require precision. If the second stage engine lights while still in contact with the first stage, exhaust gases can cause catastrophic damage. The solution was simple but vital: add a longer delay between shutdown and separation, ensuring the first stage fully stops before detachment. This was corrected on the very next flight, Falcon 1 Flight 4, which became SpaceX's first orbital success, Falcon 9 CRS-7. On June 28, 2015, the Falcon 9 CRS-7 mission exploded 2 minutes after launch. The root cause was a structural failure inside the second stage's liquid oxygen tank. A steel strut was designed to hold down a high-pressure helium bottle. The helium bottles, known as composite overwrapped pressure vessels, are used to maintain tank pressure as propellant is consumed. The strut snapped under load, far below its expected strength rating. When the helium bottle broke free, it discharged gas violently into the oxygen tank. The rapid release of helium caused the tank pressure to spike beyond design limits. The tank ruptured, and the rocket disintegrated. This was an example of overpressure failure, where internal forces exceed the tank's material strength. The explosion destroyed thousands of pounds of cargo for the ISS, including scientific experiments and the first international docking adapter. Afterward, SpaceX mandated that every strut be tested individually to full load, using stronger steel designs to eliminate weak links. Falcon 9 AMOS-6. On September 1, 2016, Falcon 9 exploded during a static fire test at Cape Canaveral. This was one of the most puzzling failures in modern rocketry because it occurred on the ground, without engines firing. The issue lay in how liquid oxygen and helium interacted. To increase performance, SpaceX used supercooled propellants. Liquid oxygen chilled below its normal boiling point. During fueling, helium bottles inside the oxygen tank were rapidly filled. As helium expanded into the bottles, the surrounding carbon fiber overwrap trapped small amounts of oxygen in microscopic gaps. This oxygen froze into a solid state. Under pressure, the carbon fibers rubbed against the oxygen crystals, creating friction that caused ignition. Once the oxygen ignited inside the tank structure, the helium bottle burst, and the tank exploded in a fireball that destroyed the $200 million satellite. This event revealed a little-known danger of cryogenic fueling, the interaction between solid oxygen and composite materials. SpaceX redesigned its helium tanks and changed fueling procedures to avoid trapping oxygen in carbon overwrap. Falcon 9 landings. Between 2015 and 2018, multiple Falcon 9 boosters exploded during landing attempts. While the rocket successfully launched payloads, recovering boosters intact was still experimental. Key failure modes included hydraulic depletion. On one early attempt, the rocket ran out of hydraulic fluid needed to move its grid fins, which guide the booster during re-entry. Without steering, the booster veered off course and crashed. Engine instability. On several occasions, the center Merlin engine used for landing produced unstable thrust. Small timing errors in ignition caused the booster to slam into the deck or land too hard. Velocity miscalculation. In rough seas, boosters landed with too much horizontal velocity, tipping over and exploding. Each failure provided critical telemetry. SpaceX upgraded boosters with larger hydraulic reserves, added more precise engine throttling, and reinforced landing legs. By late 2018, these refinements led to regular successful landings, paving the way for routine reusability. Starship SN1. On February 28, 2020, the Starship SN1 prototype was tested at Boca Chica, Texas. Engineers filled its tanks with liquid nitrogen to simulate flight pressures. The lower tank bulkhead suddenly collapsed, sending the upper section flying off before exploding on impact. The failure was due to structural weaknesses in the welds. Starship's tanks are enormous stainless steel structures, and the welds connecting bulkheads must withstand immense cryogenic pressure. In this case, the welds were too thin and the geometry of the tank allowed stress to concentrate at the bulkhead joint. When cryogenic fluids are pressurized, even a slight design flaw can cause the structure to buckle. SpaceX responded by switching to stronger welding methods, thicker bulkhead designs, and improved inspection protocols. Starship SN4. On May 29, 2020, Starship SN4 exploded after a static fire test. The Raptor engine fired successfully, but as venting began, a methane leak ignited. Methane is highly flammable, and any spark or hot surface nearby can trigger combustion. The explosion originated from ground support equipment rather than Starship itself. Faulty connectors in the fueling lines allowed methane to escape. Once ignited, the leak caused a chain reaction that destroyed the vehicle. This failure emphasized that rocket safety is not only about vehicle design, but also about ground infrastructure. SpaceX redesigned fueling quick disconnects, valves, and venting systems to handle methane more safely. Starship SN10. On March 3, 2021, Starship SN10 completed a dramatic test. The prototype ascended to 10 kilometers, executed a belly flop maneuver for aerodynamic braking, and reignited engines to land upright. It was the first Starship to survive touchdown, but only briefly. A methane leak at the base ignited a few minutes after landing, causing a delayed explosion. The failure was linked to engine plumbing and venting design. Because methane is stored at cryogenic temperatures, leaks can occur when seals contract or frost builds up. If unvented methane pools near hot engine components, ignition is almost guaranteed. While the explosion destroyed SN10, it proved that controlled landing was achievable. SpaceX focused on upgrading methane venting systems, insulation, and thermal protection to prevent fuel buildup in later tests.